Okay, so first I'm going to pause on this. So cross-sectional area, what does that mean? So a cross-sectional area is a two-dimensional area that comes from a three-dimensional figure. So it's super hard to draw these kind of things, but if I have a plane, like if you think of the ceiling as being a plane, the wall with the windows is a plane, the wall with the board is a plane, the floor is a plane, your desk can be a plane. So a plane is a two-dimensional flat surface, but it goes forever in all directions. So if I have two planes, they can intersect together in a line. So that could be the crease where two walls meet in the back corner and the front corner, or it could be the line where the ceiling and the front wall meet, or creates a line. If you have three planes, they could intersect at a point. So if you think about like the corner of the room, like if you look above the flag, there are three planes with the wall with the windows, the front wall, and the ceiling. They all intersect at a single point. Or I could have parallel planes. Parallel planes would be an example of the ceiling and the floor, or the front wall with the television, and then the back wall with the bulletin board, so they never touch. All right, so we have solids. We've talked about solids the last couple days. We can also call them polyhedrons. Won't really call them too much of that, but it's a solid with flat surface that the surfaces are polygons. So we can have rectangles, triangles, quadrilaterals, whatever type you want. Okay. So, again, just a little review. We have prisms. Prisms have two bases and rectangles that go around. A pyramid has one base of a polygon and has triangles that go around. A cylinder, it has circular bases, two of them. If you were to unwrap the cylinder, think of like a soup can, it would be a rectangle. And then a cone with one circular base. If we were to unwrap this, it looks kind of fancy. We'll talk about that. Okay. So cross sections. Cross sections occur when you take a solid. These are all looking at cylinders, and you slice it, and you look at one section of it. So the questions that you'll see on the milestone will ask you to identify what kind of shape you would see from a solid. So I can take a cylinder and I can get a rectangle out of it. I can get an oval out of it, or I can get a circle out of it. Those are really my only three options that I have in dealing with a cylinder. I don't know how to pause. All right, so I would like for you to look at other shapes and see how they would get you a cross-sectional area. So I've got some practice with that. But if I go back to Cavalieri's principle, you write this down. So for Cavalieri's principle, so let me just read. In other words, if two figures have the same dimensions, height, radii, base, etc., whatever they happen to be, but they are just slanted or oblique, then they will have the same volume as if it was not slanted or oblique. So if I look at these two prisms, they have the same shape as the base. They have a hexagonal base. So these are hexagonal prisms. They have the same base, and they have the same height. So the height here is the same as this height here, but not the slant height. This in the center represents a cross section for each of them. Here I have a rectangular prism. These bases are also congruent. This height is the same height as this. The slant height is different, but the actual height on the inside is the same. And these are congruent cross sections. If I look at a cone, if I were to take the tip of the cone and just move it over to the right, same height, same radius, they're going to have the same volume. This is a stack of CDs. If I have a stack of CDs and I just slant it over, it's going to have the same volume as putting it back together. So if I look at these examples down here, we're going to compare. You're going to see a lot of comparing questions in the milestone with this. So we're going to use Cavalieri's principle to determine which solid has more volume. So I need to look at the heights of each of the items. So if I look at this rectangular prism, the height is 20 inches. If I look at the height of this triangular prism, its height is also 20 inches. So based on Cavalieri's principle, we have the same height. Now I need to look at the area. So the area of the cross section for this is a rectangle. So the area is going to be the base times the height and the length times the width, which is going to end up being 24 inches squared. If I look at this cross section, which is a triangle, so I need 1/2, and it's a right triangle. Here's my base, here's my height. So 8 times 6. 8 times 6 is 48. If I half that, I get 24 inches squared. So based on Cavalieri's principle, if they have the same height, whether it's straight up and down or oblique, and they have the same area of the base, they're going to have the same volume. So we're looking to see which one has more volume, and I would say they have the same volume. So I'm going to write a sentence. So these solids have the same volume. I'm going to list out a little reason why. So because they have the same height, and I'll put base area. So again, like on the milestone, they're going to ask you to use Cavalieri's principle. You don't need to memorize it word for word. You really don't need to like know how to spell his name, but you need to be able to recognize his name. It's going to look at you to compare two different shapes. You need to look at their heights and their cross-section areas or their bases and make sure that they are the same, and then they will have the same volume. So you have some homework here in dealing with cross-sectional areas and making these kind of assumptions with different solids, and then also using Cavalieri's principle. Remember, tomorrow is our magnet symposium, so please dress professionally and come with a good attitude and ready to have a good time, and you're really going to enjoy Wednesday. See you tomorrow.